In this video, I introduce a non-volume preserving generative models. Given observe a variable x and apply a probability distribution pz on latent variable z, we define a bijection transformation f from x to z with the inverse g. Using the change of variable formula here, the log likelihood on x is defined as a sum of two terms. The first term encourages contraction of the latent space, namely we use a less number of latent variables to express the latent space. The second term encourages expansion and penalizes contraction. Non-volume preserving means the second term is not equal to 0. Here, this is the Jacobi matrix of f at x. A coupling layer defines the invertible transformation f with easier computation of a Jacobi determinant. By splitting a vector into two blocks, the affine coupling layer has output y1 to d and yd plus 1 to capital D. Namely, we use x as input to calculate output y through affine transformation. For example, input is x1 and x2. Output is y1 and y2. y1 is equal to x1. y2 is computed from x1 and x2 through affine transformation. X and t are scale and translation. Here we use a convolutional neural network to estimate S and T by using x1 to D as input. This operator is an element-wise product. The Jacobi matrix of the transformation F above is a triangular matrix. This is the identity matrix, and this is the diagonal matrix. So from this diagonal triangular matrix, we can easily calculate the Jacobian determinant here. A reverse mapping of a transformation f is written as this formulation, namely, we use y1 and y2 as an input. The model generates output x1 and x2 through inverse affine transformation. If we use a binary mask B is used to split a vector into two groups. A unified output y is written as one formulation. The spatial checkerboard pattern mask has a value 1, where the sum of spatial coordinates is ordered. Otherwise, 0. Namely, the white grid corresponds to B is 1, and a black grid corresponds to B is 0. The forward transformation leaves some components unchanged, which can be overcome by using alternative pattern. Using the relationship here, the combining Jacobi is written as a product of two transformations, f1 and f2. For example, input is x1 and x2. First, y1 prime is the same as x1. We use x1, x2 calculate y2 prime through affine transformation. And then this y2 is the same as y2 prime. And we use y2 prime and y1 prime to calculate y1 through affine transformation. And namely, both x1 and x2 have contribution to the output y1 and y2. The reverse mapping is computed by product of inverse transformation f1 and f2. For more details, please check with these references. Thank you. Bye.